Hey guys. All right. In our last lecture here on the birds is adaptations for flight. So what is it? We've already talked about a couple characteristics of what helps with flight, but what is powered flight itself? Do we really need to be able to actually fly? So a powered flight is going to have two primary requirements that we're going to really need. The first thing is the obvious one, being able to actually get off of the ground and into the air. So we're going to need enough lift. If you look at the images here on the right, so we're going to need enough lift to be able to go upwards and to be able to overcome gravity, which is something that's pulling us downward. So that's in downward force. Then we're going to need enough thrust to be able to keep moving forward while trying to overcome all of the friction, which we call drag, which is trying to push us backwards. Very similar to a car. So when you're trying to drive faster speeds, there's a wind, or if you're running really fast, or if you've ever been on a bicycle and going down a hill, you're going to feel all that wind. It's going to eventually, if you stop pedaling and if you started coming to a flat ground, you'd start slowing down. So the other characteristic or component to powered flight is then obviously the ability to stay in the air. And this will require huge amount of physiology and biomechanical demands and lots of energy to actually maintain your body in there. The other type of flight, though, is gliding. So in terms of gliding, this is mostly a passive process. This is like what you're seeing here in the very bottom portion. Here's kind of a flying squirrel. What they do is just have kind of sails. You've seen people go skydiving, so they'll sometimes have these kind of sails as well too. Here's me going paragliding. Okay, you don't see the paraglide itself, which is up here. We're just hooked into the system, and the GoPro camera was on one of the wings. Or sorry, hang gliding, paragliding, very kind of similar to that. So there's a passive process where it's relying on kind of external forces to keep you floating and just maintaining within the wind column of seeing whatever you can. But it doesn't actually have thrust to it unless we were to add like rockets behind us, right? Which is sort of what planes ultimately end up doing. So gliding is something that you'll be able to go from perhaps one area to the next in short term, but you're for the most part always going to be moving your way downwards. You're never going to really be able to go back up again in terms of like flapping. Powered flight is what then allows you to have that upward lift. So is powered flight unique to birds? Absolutely not. People think that that's the only thing that can fly around on the planet. Mammals have flying animals, bats, right? Dinosaurs, well, obviously in this case, birds. Cousins of dinosaurs were pterosaurs, so that was the first terrestrial animal, other than for insects, that was able to fly, so the kind of large-bodied vertebrate. And then, of course, as I just said, insects. And there's tons of insects that do a lot of that flying. So this is a convergent trait. This is not something that we can use in a phylogenetic context to try to be able to match things up. This is a completely convergent trait. Very analogous. So what are the advantages of flight, right? If I asked you this in class, you'd probably list many of the things that we have here. Escaping from predators, or be the opposite, being able to catch your prey. Perhaps maybe for a butterfly or a bat, it might be to help them get some nectar, so therefore they can use that for their food materials. Traveling, that's a pretty obvious and given one. Accessing other food sources, and perhaps then redirecting the use of their legs and feet for something else. In this case here, to be able to have it more for grasping versus their arms become the wings, right? So it's a little bit different than what we do with our limbs. We use our hind limbs for movement, so our legs for movement, and our arms for manipulation. Whereas birds will use their feet for manipulation, whereas they use their arms for movement, right? So they've kind of flipped that. There's some overlap here and there, as you can imagine, but they've completely changed that up. So any animal that has powered flight very much does it in this case. So then what are the adaptations needed for powered flight? We've seen a lot of these throughout the semester, but we're going to reiterate them and add a couple new ones here that you might not be familiar with. So the first thing, wings. That's pretty obvious, right? They're really nice and tasty. If you put some buffalo sauce on them, But what is it that they have anatomically that helps us? So each next time that you're eating wings at some kind of on Super Bowl Sunday, this is what you want to think about, right? So a couple things is that their forelimb starts to fuse. So let's look at this image here on the right. Here we have our humerus, then our radius and ulnar. These are the major forelimb bones that we still have. But then all the different carpals and phalanges and other things, they all fuse up to the point where modern birds only have, think of it as like 2 fingers. They have this one here, which is just an extension and just a fusion of it, and then this little tiny one here. So they reduce the amount of digits, they fuse all that stuff up, and by doing so, they elongate that forelimb as a pre-adaptation for more and larger extent of that sail in the form of feathers. The next thing that they do is, in terms of their skeleton, they start to stabilize a little bit more of it. So they start to fuse other bones together as well too, like we've seen, like the pygostyle. They do the keel here, so they fuse that up as well too in terms of the sternum as well. Their sacrum is really significantly fused up of where their pelvic girdle is. But they also have these structures that are very novel to them called unicate processes on their ribs. And so here is a rib right here where the outlining with the cursor. And with the yellow arrows, I've pointed to these unicate processes, these little kind of dinky things that are sticking upwards. That's just another spot for more muscle and soft tissue attachment of different ligaments and things. Because with the powered flight, there's going to be massive musculature in this breast area. So whenever you're eating a chicken breast or turkey breast, that's that massive muscle. And so those muscles need more areas to attach to or have ligaments to attach to them. And so we form these unicate processes to help out with that. The other thing that they do is that they will have a derivative of their epidermis. So our top layer of the skin into something like a lizard scale. So the idea of this is that it's been hypothesized as either being a homologous to lizard scales or perhaps develop into endothermy. There's still more research kind of coming out on this, so they'll probably rewrite the textbooks in the next few years or so. But something that kind of ultimately comes from this is that it's a derivative that evolves that we see as feathers and different types of feathers, right? So via the feathers that we were kind of seeing in earlier groups, here we start taking the feathers and we start modifying them into different formations and different structures to then ultimately have not only downy feathers for insulation, and contour feathers to kind of cover the body for a little bit more insulation. Perhaps maybe those are the ones that have some coloration patterns to them as well too. You see a contour feather over here, so it's not really great for flight. The flight feathers are the ones that really modify significantly. So they start having a central structure called a calamus and a rachis. They have these various different veins, lots of barbs and barbules and hooklets and all these things. So therefore, there is a really good structure to it, really good, almost like a tarp or parasail, so it doesn't just break apart right away. So how did feathers evolve? We've seen this a little bit before, but this is a nice good figure to go through this as well too. This kind of primordial version of kind of like a Maniraptor looking dinosaur here. So we see that there's some smaller downy feathers, perhaps a little bit around the tails as well too. Nothing around the arms, kind of around from their armpits and down the bottom on the sides of the arms, but nothing really for flight, right? So where did these feathers evolve? If you follow this key here, the forearm wing feathers or the forearm wings themselves are shown in like a W formation, and the different types of feathers from downy feathers to more specific types of feathers for flight. If we look at Saurischia, because ornithischians don't have any feathers. So if we look at Saurischia, sauropodomorphs don't have any. Okay, so we don't have any evidence of them, so we don't have to worry about it. So probably downy feathers started to evolve somewhere over here in Theropoda. So we definitely know that Tyrannosaurids, Compsognathids, things like that will have these. Ornithomimids start to have some form of a wing, but not necessarily for flight. And so there is potentially some convergent evolution that's going on here. But then as we get further and further, we start seeing a consistent pattern, right? All the various different types of feathers and a wing eventually for powered flight. So a few other adaptations in terms of the requirements, we have the musculature. So these breast muscles that you will be eating, the chicken breast, the turkey breast, whatever it is, during Thanksgiving. So these are going to follow along with that keeled sternum, and that furcula is going to be helping with that as well too, the wishbone. So the two muscles that I want you to know of are the supracoracoideus and the pectoralis muscles. The pectoralis are really what you're actually eating in terms of the chicken breast. The supracoracoideus will tend to be like the dark meat that's underneath that area. But these will be massive. If you look on the bottom right image here, it's probably that of like a pigeon or something like that, or like a dove. This keel, right? That's what we were talking about with the sternum. That is what significantly expands and allows for those muscles to attach to there for that powered flight. We need the muscles to move the body. Otherwise, it's not going to be able to lift those wings and move them around constantly. So the other thing that they evolve is a lot of other evolutionary novelties within the other parts of the, not just the skeleton, but the other organ systems. So for instance, respiration. Because you are going into the air, you now need to modify the way that you are taking in oxygen that you need to perform cellular respiration. So therefore your muscles can actually have that oxygen and form this structure called ATP, adenosine triphosphate, which is sort of like cash. And that is what we use as energy to allow our bodies to be powered. So for powered flight, this is the most energy or the highest energy expenditure activity that you can do of any animal. So we need lots of it. So what do? They actually form some air sacs. Not only does that reduce the amount of weight on the inside of their body, but the way that they go about this is that they make sure to utilize as much of the air as possible. So all the oxygen, so therefore what they're breathing out is almost pure carbon dioxide, and there's no oxygen left over in there in terms of the chemistry composition of those two gases. So what they do is that they'll, and for a breath in, normally for us, we'll breathe stuff in, it'll go into our lungs, we'll use as much of that oxygen as we can, and then we'll breathe that stuff out, whatever's left over. No, they do a little bit different. They'll breathe things in, that'll go into one air sac, so fresh air. And as they then exhale, this material will make its way into another air sac that is used air. New stuff goes into, let's say, air sac A. And then each time that they breathe out, that material goes into air sac B. Then finally, from air sac B, as they exhale, then that material will exit its way out. So they're kind of similar to what cows do when they're kind of chewing on their cud. So they will kind of regurgitate some food, pretty gross, but it's what they do. And then they will try to chew it back up again so they can get as much out of that material and as much nutrition as they can. That's sort of what birds are doing here. They're trying to get as much of that oxygen as possible. So therefore, it's as efficient of a respiratory mechanism as they can be. In terms of circulation, they also significantly change themselves. So if we look at evolutionary pathways of how the circulatory pathways, so your heart and your blood vessels form, this is we discussed a lot more of this kind of stuff if you're really interested in a course called comparative anatomy. And so in this case here, if we start off with fish, they have one circuit. It's like an Indy 500. They have got two chambers to the heart, just a single ventricle and an atrium. We're not going to get into what those all do in this course here, but that blood will just make its way and it'll filter through the body and it'll just continuously go out as a circuit. Frogs change that up a little bit. So they change up the heart. So therefore now we have kind of a dual way because they can breathe externally while also breathing cutaneously through their skin. Not all of them, but to some extent. Then turtles and lizards start to change this up even more so to the point where crocodiles are very similar to our condition, where they have a four-chambered heart. The blood vessels run a little bit differently, but the heart is similarly structured. So birds have a four-chambered heart, just like mammals do. And so this is very different than most other lizards, where they will have some of their oxygenated and deoxygenated blood intermixing in their heart, which is a bit inefficient, but they're not as active. They're also exothermic, meaning that they rely on the outside temperatures to then help warm their body up. For birds, they are very much like mammals, where their circulatory system is almost identical to us, but we have evolved that independently and convergently. So now if you're wondering, what about dinosaurs? What kind of circulation pattern did they have? It was probably somewhere in between here, depending on the type of behave, or I don't want to just say behavior, but the locomotion pattern that they had. So if they were more closer to birds, probably had something more of a four-chambered heart like this in terms of their physiology. If they were more closer to like the duckbills and ornithischians, I don't know. We actually don't have any evidence. My guess is that was perhaps maybe something along here, similar to crocodiles or something like that, maybe to some lizards. But until we find some kind of soft tissue evidence of something like that, we have zero idea. Um, but actually, I'll go back. Um, we have zero idea of their anatomy of the heart, but we do have some idea in terms of their physiology, whether they were what we used to call cold-blooded or warm-blooded. So now we use exothermic and endothermic. Is that there was a gradient, but some and probably a good chunk of dinosaurs were somewhere around like what we call mesothermic, so in between of something that would help them with the external environment warming them up, and then also being able to maintain their own body temperatures. A lot of that research is actually taken in from a lot of the histology research that, so for instance, some of the research that I do that we've talked about before. Um, and just understanding that if you have such a large animal, okay, is walking around like a sauropod, it will need to be able to maintain its own body temperature to some extent, so that way it doesn't die with fluctuations of temperature from a daily basis. All right, and then lastly, the other major adaptation is the lightweight skeleton. And this is something that we see convergently in animals that do have flight. So same thing with bats. We'll do the same thing as well. We're only showing the Archosaurian tree here. So therefore, the Pseudosuchians. So we have our crocodilians and other examples towards the very left here as an outgroup. We've got our closest cousin to dinosaurs, the pterosaurs. They also had that lightweight skeleton because they had the first powered flight of any major vertebrate animal on the planet. And then, of course, nothing in ornithischians. So we see that within Theropoda and Saurischia, that it's a pretty consistent thing. Sauropodomorphs had quite a bit of lightweight adaptations to the skeletons. So we can link those together, but not necessarily as a whole characteristic across all animals. All right, so that ends this lecture series. Make sure to complete any assignments and quizzes, and we'll see you in the extinction.